Okay, so let's move on to another mission, the InSight mission to Mars. And we've been talking about this a lot since it landed right around Thanksgiving last year. And InSight is designed to probe the interior of Mars. It's got a seismic experiment, and it's got a heat flow experiment to determine how much heat is escaping from the interior. And there's just a nicer view of that. Again, the spacecraft itself was constructed here in Denver at Lockheed Martin. So we seem to have a pretty high profile certainly in the planetary business, but as well as the human exploration business. So this is back in early February. This is a view from a fisheye camera on board the lander. This is the seismic experiment, which was deployed in January, and then this is the heat flow probe, which was deployed in early February. That's one of the foot pads of the lander itself. So this is a view from a camera on board the robotic arm, which was used to move these devices onto the surface. And so that was when the heat flow probe was set down. And I've got a movie here in just a minute showing how this is designed to work. There's it's called the mole. It's sort of a pile driver system that sits inside this chimney. It's about the size of a turkey baster, and it's got a little weight that bounces up and down, and it slowly drives the pointy end of the turkey baster into the surface. And it was designed to burrow about 5 meters down, so something like 15, 16 feet beneath the surface.
The seismometer we have on Mars is fantastic. It's operating as well as we could have dreamed. It's exceeding expectations. The goal of InSight is to understand the structure of the planet of Mars. And the primary way that we're going to do that with InSight is by measuring Mars quakes. ETH Zurich is leading the international team that is checking all of the data as it arrives every day and trying to detect and pass on the information that Mars quakes have actually occurred to the science team. We're down here in the simulator room of the Swiss Seismological Service, and we're here today to show the first example of replaying the first events that we've recorded from our seismometer on Mars.
So let's start with what we know, which is an earthquake. An earthquake from Switzerland takes 30 seconds and has very clear onsets, as we'll see.
So this Swiss quake, we'll start with the P wave that you feel there, and then in a few seconds we'll hear the S wave arrival. Slightly bigger. So that's the classic type of wave arrivals that we were hoping to see on InSight.
Next thing is one step more exotic, which is the moon. So we load a moonquake into our system and see how that feels.
This is the SP recording it, so there's no...
Yeah, is there an error ended on that?
Yes. Slowly getting bigger.
The signal is very different. We have a much smaller attenuation of the seismic waves, but at the same time we have a very strong scattering, which means that the shaking will go on for tens of minutes or maybe up to an hour.
Next thing we load into the system are the mass quakes, which were discovered by the Mass Quake Service recently. We want to know how they feel on the scale between the Earth on one side and the Moon on the other side.
On Mars, we so far have seen 2 families of quakes, and so there's a higher frequency one, and this one that we experienced now was more the low frequency version. We think this is probably pretty far away. The motions that we have here are amplified by a huge factor so that we can even see them, because on Mars the amplitudes are extremely low.
Mars isn't as simple as we might have hoped. The ground motion is not like we see on Earth. It's sort of a halfway house between Earth and the Moon. We're really trying to put the various events in place. It's a big jigsaw puzzle at this stage, and we have a long way to go before we understand it, but it's extremely exciting at this stage.
Okay, so the good news is the experiment is working. They've actually detected a handful of Mars quakes. They're working very hard to interpret them, to determine how far away they were. Are they impacts on the surface? Are they landslides? Is it faults cutting loose? And so I think the next animation talks about the heat flow probe, of how it was designed to work. And so this is just a fly around. There's the seismic experiment. The heat flow probe is sitting on the surface. They're tethered to the lander. These flat ribbon cables are where the data flow back and forth between the lander controlling them and the data that's collected. And so here's the heat flow probe, and or the whole device. And I think we'll look on the inside here. Did I just stop it? No, I'm sorry. So it's showing you the mechanism for reeling the tether as the probe buries itself in the surface. So here's the turkey baster, and it's completely inside that housing. And dramatic pause. Here's the weight that it's spring-loaded, and it sort of pulls it up and then forces it down. And so with each stroke, it should burrow a little deeper into the surface. And this is the way it was intended to work, that it would get down about 5 meters or so. Every 10 centimeters along this cable, there's a temperature sensor, and that allows them to determine how the heat is flowing from the interior. There's also heaters on the mole itself, and so they can heat it up with a known amount of power. They know what the temperature should be of the probe, and then they see how that pulse of heat transfers up to the surface. So that tells you a lot about the material that the regolith, the loose surface material is made of. So that was the way it was supposed to work. Unfortunately, what happened, they realized fairly quickly, is it only penetrated about 30 centimeters. So 10, 11 inches down, and then it stopped. And they've tried multiple times to start it up again and let it hammer, and it hasn't progressed. And so they took several months off trying to figure out what the issue was, whether it was that they'd hit a rock. If it was small rocks, it should have either pushed the rocks away or sort of tilted and moved itself out of the way. So that was a puzzle. And I think we have an interview next with an engineer at JPL who's been coming up with the plan.
Hi, I'm Troy Lee Hudson. I am a member of the InSight science team and the instrument systems engineer for the HP Cubed. InSight is a mission to study the deep interior of Mars. It has many science instruments to do this, one of which is HP Cubed, a sort of planetary thermometer. A key component of HP Cubed is called the mole, sort of a self-hammering nail that drives its way into the ground. And when we first commanded it to do this penetration, it did so beautifully, but at a certain point, it stopped making forward progress. This is a full-scale model of the HP Cubed support structure. The mole started out in this vertical tube, and when we commanded the mole to start digging, it released and started making progress, millimeter by millimeter, into the ground. At a certain point, it began to tilt, and around here, approximately 10 centimeters above the surface of the ground, it stopped making progress. So at this point, we believe the mole is still partially within the support structure, pointing at about a 20-degree tilt to the southwest. It could be the case that the mole has encountered an external obstruction, like a rock. But another possibility is that the soil at InSight is providing us less friction than we expected, and the mole needs friction to make forward progress. JPL, working along with DLR, the German space agency who provided the mole, have been trying to understand what the problem is and come up with a plan of action. We can't get a clear picture of what's happening with the mole. The support structure is in the way, so we need to pick up the support structure and move it elsewhere. We've been practicing that lift here in the test bed with models of the arm and the support structure. The lift has to be done carefully in 3 stages, small moves, so we can look at the data and, among other things, ensure that we're not inadvertently extracting the mole. Once we move the support structure and get a clear view of what's going on with the mole, we want to use the robotic arm again to help it. Our first choice is to come in with the scoop on the robotic arm and press flat on the soil above the mole. This may increase the friction at the mole, giving it that extra nudge it needs to start making progress. This is unexplored territory. The mole is going somewhere we cannot see and have never been before. To get that crucial number, the heat flow of Mars. As a scientist, I want to get that number. And as an engineer, I want to see the instrument we've worked on for a decade do the thing it was designed to do.
Okay, so what the plan is to lift using the robot arm, to lift the support mechanism off of the mole itself and do it in multiple stages. So you can sort of see under the structure when you lift it by that fisheye camera, which is off to the side. And the point of doing it very slowly and carefully is they're afraid that the top of the mole is stuck inside the support structure, in which case, as you lift the whole thing, you'd be pulling the mole out of the surface. They have no provision for repositioning the mole if it isn't in the surface. There's no way to wind it back into the support structure. So if they do that, it's game over for that experiment. If they determine that it's hitting a rock and it can't get around it, then there's nothing they can do about that. But this idea of the texture of the surface, the cohesion of the surface being much less than, well, the cohesion is higher, the friction that it provides is much less than what they expected. That's what the whole purpose of this. And to explain that, imagine you have, say, 2 cereal bowls or coffee cups or whatever. You fill one with salt or sugar, something like that, or sand, just loose sand, and you fill the other with something like talcum powder or plaster of Paris. Take a pencil or a pen and insert it in both of those materials and then try to pull it out, and you'll see on the sand or the sugar or salt, it just collapses in on itself. It doesn't leave a hole behind. That's because the material is not very cohesive, so it doesn't stick together. But that's what they designed the mole to do, is assuming that it's in contact with the surface material, and that provides a little bit of friction. So when that pile driver hits, it stays at the low point of that stroke rather than just bouncing back. The other material, the really cohesive stuff, plaster of Paris, talcum powder, when you insert the pencil, pull it out, it leaves a hole behind because the material is actually cohesive enough, it sticks to itself, and it's not necessarily sticking to the probe. And you can imagine if this is sort of bouncing around, it could be rotating a little bit, and it just makes a bigger and bigger hole. And so the mole wouldn't even be in contact with the surrounding material necessarily. So that's what the hope is. And this is just a graphic of how they think it was positioned. So it's at an angle of about 20 degrees. Here's the structure. There's the cable coming back. And so what they did was attach the arm to this structure and very slowly lift it so that they could see how the mole was positioned. And this is a view from that fisheye camera, so let's cycle this. So there's the structure being lifted, there's the mole, and there's the cable. And we'll get a better view here from the robot arm camera. And so there it's picked it up. It's moved the whole structure about 10 or 12 centimeters back toward the lander. And there's the mole sticking out of the surface. There's the ribbon cable. And the first thing to notice is there's a hole around it. So that's more or less what they were hoping to find. Still doesn't necessarily say that there isn't a rock, but let's look at a few other pictures here. So the intent, and this is in the lab back at JPL, here's the mole sticking out of the surface. This is a little sample scoop on the end of the robot arm, and what they intend to do is push down onto the surface with the arm and use as much force as they can, and the hope is that will collapse the hole and provide extra friction for the mole. And so once they do that and get it in the right position, then they'll turn the pile driver back on and see what happens. And so they completed this step, the step of moving the structure away the end of June, and they've spent most of July trying to decide exactly how to do this. And so this is just an animation of individual images showing them repositioning the arm to get near the mole. And then here's where they were last week. And so there's the mole, there's the hole. These were the foot pad prints, and here's the sample scoop. By the way, the sample scoop it's just serendipity that it's even on board. The robot arm was a leftover from a mission in 2001 that was being built by Lockheed Martin that was canceled. It was after we lost the two Mars missions in the late 1990s, and they decided to forego the 2001 lander that had already been designed and was undergoing construction, and they moved, sort of leapfrog, to do the Mars exploration rovers, Spirit and Opportunity. And so they had this arm left behind. It had a scoop on it. There was no intention to use that for anything on InSight. They have no instruments that will be able to analyze the materials you'd collect, but now it turns out it's nice to have something just to use as a surface to press against the regolith. And so here we were 6 days ago. Today is day 240. And so here was the next day moving in, and the sun angle is somewhat different, so you can actually see inside the little hole here. And it seems like material has already collapsed in it, even though they haven't touched the surface with the scoop. And here they were this morning. And so they're barely off the surface here. And then about an hour later, they made contact with the surface. You can sort of see the little disturbance in the regolith here where the sample scoop is pushing on the surface, and then they sort of moved it back a little bit. And so there's the track left behind. And so they're in the process of getting the feel for where they are. I think the goal is that they will move this around to collapse material into the void that's around the mole. They will reposition the arm to push on the surface, and then they will turn the mole back on and see what happens. So I expect by our next 60 minutes we will know if this effort has succeeded or not. I mean, if it succeeds, it should happen pretty quickly. If it doesn't, they'll probably still try various things, like maybe push on the mole itself as opposed to being just off the side of it. So that's where we are right now, and keep your fingers crossed.